Hi, my name is Matthias. I work at SoundCloud. I'm in the production engineering team, which is just as fuzzy as the name suggests. I'm a bit of a generalist in that I've been in the teams that handle the infrastructure in general, and many of the things that have touched many things that much of the glue that holds our infrastructure together. And one of these pieces of glue is load balancing, though. So what I'm talking about is internal load balancing mostly. Many other companies have talked about how they get users' traffic into their data center. This is more about how you get it around inside your data center. Between your apps and your databases, between apps and apps, between databases and apps sometimes. So we'll look at three basic components that make up our toolbox. And this is not just to be clear, this is not a generic talk about load balancing in general, or even a general talk about HAProxy or IPVS. This is very specifically about how we use them and what worked for us. And I wanted to share this story because I think this would also work for many other people. And all these components are freely available. This is all open source. We built none of this. We're just plumbing together pieces of the internet. So over time, we have converged on three basic technologies: HAProxy for HTTP load balancing, IPVS for super high throughput layer 4 switching, and DNS service discovery wherever we can. And we'll get about which, when, and where. Next. Good. So let's look at the evolution of a load-balanced application. This is somewhat simplified, but basically the app in question here is what we lovingly call the mothership. This is our Rails monolith. SoundCloud started as a single Rails application, and so that was around 2008. It's still around. We still use it. We start breaking out a lot of functionality from it. So it's still core, but it no longer bears the brunt of our business logic. It has some special requirements when routing traffic to it. For example, a single instance of it, a single thread, can only handle one request at a time. If you try to send another request at the same time, you will immediately get an error back. Because that's how Rails with MySQL worked back in the days, and we never had the time to fix it really. So we, because this is a huge undertaking to make a whole Rails app re-entrant, we never went there. We worked around it, we routed around it, and we used these load balancing tools to deal with this. So every application starts as a single instance on a single computer somewhere. We added an Nginx on front of it to serve as to do request buffering, so that already gives you a big increase in usability because the app doesn't have to wait for your slow computer or remote computer to download all the things that it's sending. It can already serve the next request while Nginx has it buffered. And Nginx can serve static assets that don't actually need to run code because it's really good at that. The next step, obviously, is, well, just run more than one instance of this app and tell Nginx about all of them and let it deal with that. This kind of works until it doesn't, because Nginx is not a load balancer. Nginx is not, you have some level of control how it sends traffic to these backends, but not a whole lot. And especially, it can't fulfill this requirement of only send one request at a time. It just, yes. If someone knows how to configure Nginx to do that, please tell me. I never managed to. And it's really easy to do with what we ended up then using, HAProxy. So HAProxy is a generic load balancing software. It can do HTTP and it can do TCP. In this case, we use it in HTTP mode, and we just put it between the Nginx and the application. Nginx sees a single app again, and the app only gets requests as it needs to. So let's take a closer look at HAProxy. HAProxy is really, really good at relatively short-lived connections. When your connections live for a very long time, you run into issues with reloading the configuration of HAProxy itself, because it doesn't actually reload, it does like a restart in place, and the old instances hang around, like the old processes hang around until the last connection is closed. Because of a pathological case, we ended up with, at some point, we ended up with hundreds of HAProxy processes on the same machine, all waiting for the last connection to finally die, so they can finish. So anything that's reasonably short-lived, that's much shorter than the cycle at which you're reconfiguring, HAProxy is fine. It gives you really good telemetry, much, much better than open source Nginx, I have to say. In the commercial version, you get really good of Nginx, you get really good metrics as well. In HAProxy, you get them for free, down to the per backend level if you choose to. You can see like which backend through how many errors at which point in time. It's really good at traffic control and queuing, so that's only this many requests at once per backend. And then it can queue up to a certain point if there is a momentary spike that just exceeds your capacity. Keep in mind, queuing does not make more capacity. So if you're just running under capacity, your queues will always be full and you will always drop requests. It only helps you deal with a very short spike. And it can do some basic layer 7 routing. We'll see how that works. It's definitely not as good as Nginx at that, but it's good. It's been good enough for our use case. So we ended up in the end replacing all the routing logic that we had put into Nginx configurations. We removed that, and I removed it into the app where it's actually part of the business logic, or we moved it into HAProxy where it's just about path prefixes and host names. It's not so good at long-lived connections. We talked about that. Very high data throughput. You're limited by the throughput of the NIC on your machine. That's pretty much the limit with HAProxy. You have to get the traffic in and you have to get it out again, and a single machine can only do so much. With multiple HAProxy processes, you can totally saturate the NIC on your machine. That's like it can easily do that. HAProxy is not the bottleneck here. And it's not a web server, so it doesn't do static asset hosting. And it doesn't do request buffering either. So depending on what your app looks like, you may want to have an Nginx in the stack somewhere as well. Because of the way our apps evolved, we mostly don't need that anymore. So here's an example of how the backend, how the simple vhost routing works. With HAProxy, basically you're kind of abusing ACLs to direct traffic to one or the other backend. There are plenty of examples on how to do this on the internet. I just wanted to put it here to illustrate what you can do. So you can match headers, including the host header, and you can match path prefixes. That is in many cases totally sufficient as your web router. And then you have a default backend that just says no. So if someone comes and asks for a host that is not configured, it goes no. You can also put a real backend in there if you have a default thing that you want to serve. The one thing to know, so this is what mostly made Nginx redundant for us. One thing to note is that you are limited by, there are a bunch of connection limits in HAProxy by default that are not shown here. Read the documentation very carefully because you can drive HAProxy way beyond its default limits. So that's, we have, like, 50,000, 100,000 connections with a single handled by a single Nginx. The default is around 2,000, I think. So it will just refuse connections at that point. But if you find the right knobs, you can just configure it to go much higher. So monitoring HAProxy. Coming from SoundCloud, this is a completely different talk, but we use Prometheus a lot. The HAProxy exporter that you can use with Prometheus is really good. It gives you all the metrics you can get out of HAProxy as a time series. We had to turn some of them off because it blew up our monitoring servers to watch every single backend, and these backends have their own metrics, so we didn't need that. It gives you all the application health. It gives you the backend health if you want to. QDiff, open sessions, things you want to watch to see whether your load balancer is healthy is bandwidth usage. So if you're approaching the capacity of your NIC, your load balancer is going to get slower and you need to scale out. And secondary packets per second. If your requests are very small, you may run into issues with processing these first. That kind of depends on how powerful your hardware is, what kind of NIC you have. You need to test that. I can't give you numbers on this. Like that really is hardware dependent. Good. Multiprocess HAProxy, I just wanted to show this graph. That's the only reason this slide exists. You can run from one configuration, you can run multiple HAProxy processes. This is how it scales across CPUs. A good rule of thumb that we found for unencrypted HTTP is one HAProxy for every other CPU that you have, for every other core. So on a 16-core machine, we run 8 processes. That leaves one core to handle the network interrupts and one core to do HAProxy, and this works really well. This is how you're never gonna how HAProxy can saturate your machine. To do that, use a relatively recent kernel. The graph that is up here is when we upgraded our a fleet of load balancers from Linux 3.2 to 3.16, because somewhere in between SO reuse port was introduced, which allows these HAProxy processes to listen on the same port and share this port properly, and that. I don't know how it worked before, but it wasn't very well balanced between these processes. Now it is. So 3.16 is not too new. That's okay. Small caveat with SO reuse port, there is a very low chance that while HAProxy reloads, a few connections will get dropped or reset that are just in the process of being established. For us, this is such a low probability, and the applications that talk to HAProxy are resilient enough to deal with this, so we don't worry about it too much. But it's there. If you need 100% reliability, if that's what your CTO wants to sell as an SLA, then you can't. And you can't do that anyway, but this will also make it hard. All right, so let's go back to our application. We have our stack, we have an Nginx, we have an HAProxy. So I talked about this. We ran into the issue of, okay, so we have outgrown the capacity of our NICs. We do not have bigger machines. At that point in time, we did not have any 10 gig Ethernet machines. So how do we and we needed to load balance over these HAProxys, but how do we load balance with something that has more capacity than any single machine can have? The answer is IPVS. IPVS is a kernel module that's in the Linux kernel that can do many things. It's called IP virtual server. It can do many things. The way we use it is for layer 4 TCP load balancing with direct server return. And the way direct server return is, in the next slide, KeepAliveD, just so you are not confused why it's up on the slide, KeepAliveD is the management daemon that we use to control IPVS. So KeepAliveD knows what backends there should be, it runs health checks against them, and then it adds or removes them from the kernel table. But all the data goes through the kernel plane and never actually goes to user land. That makes it even faster. This is the slide I wanted to talk about, so we'll get back to the other one later. The way direct server return works is only the traffic that goes to your application is actually load balanced, and then the traffic that we return is not. This works really good if your responses are much bigger than your requests, which is typically the case both for a web application and its database backend. You send a query, select star from, that's a few bytes, and then you get back the whole row, that's many more bytes. So with this, we can we can scale about 10 to 1 up to 100 to 1 over the capacity of a single network interface. Because the load balancer now only has to deal with a fraction of the traffic. This comes at a cost. The network setup for this is kind of tricky to get right. Once you get it right, it's great, but it's kind of tricky. You have to deal with like tunneling interfaces and setting all the right IP addresses in all the right places, but not in the wrong places so that they don't get announced to the network wrongly. We had a bunch of issues where suddenly one database server would just try to take over all the traffic because it started posing as the load balancer. But if you need it and you do it, once you sort it out, it works great. It gives you a huge boost in capacity without having to buy big, expensive F5s. So all our database traffic, like at peak when we were still load balancing all of it, all our database load balancing happened on 4 single 1 gig machines with a return traffic of like 100 times as much. So let's look at this slide before we forget. KeepAliveD and IPVS, this pair is really good at busy connections. Because it does not see the return traffic, IPVS cannot actually keep a full TCP state machine. It can't know when the connection has been properly closed. So it's relatively aggressive at timing them out, much more than, and if you set your TCP timeouts wrong on the ends, then sometimes the IPVS load balancer has timed out the connection while the database thinks it still exists. And that confuses databases a lot. So there is some, if you run into this, if you have a busy connection, if the web app asks the database about stuff all the time, then that's fine because there's always traffic, the connection never times out. If you have if you need to keep an idle connection alive, use TCP keep alive. You tune that on both ends so that they constantly send probes back and forth. You're good. It shines when the responses are much larger than the requests, because then we can really leverage the direct server return. And it can do long-lived connections really well because the configuration reloads do not break these connections. Telemetry, you only get so much out of a level 4 load balancer. You can only know how many connections there are. That's just the nature of layer 4. So we looked at this. Monitoring. Really, we never actually monitored KeepAliveD that much. but because all the data actually goes through the IPVS layer and not through keep-alive-D, that was always good enough. You need 2 checks. One is you can get metrics about your connections from the node exporter. Again, this is for the Prometheus use case. So this is how we monitor this. But basically, all it does is it reads a bunch of files from /proc and presents them as metrics. So if you need to re-implement this for your own monitoring solution, look at the node exporter IPVS collector. It's very easy to do. Like there is not much magic to it. And the other thing you really, really need to check, and this is really important with IPVS and the direct server return, is can I reach my VIP? You just need to probe it all the time. Can I reach it? Can I reach it? Can I reach it? Because a single misconfigured real server will pass all the health checks, but not actually accept any traffic for the virtual IP, and you're down. Because the whole, we use weighted least connections, so all new connections will actually go there. Because our connections are long-lived, especially to databases, we can kind of survive this for a few minutes, but as applications reconnect, they always get they try to connect to this bad database server, and it just doesn't work. And we catch that by just monitoring it for it very aggressively and fixing it when it comes up. In this scenario, for these load balancers, packets per second are much more important than bandwidth. Because you are on the small packet side of the connection, you have to process many more packets to get to a gigabit. So we've always run into limits in how fast we can shift packets between the network card and the kernel and back. Again, you need to figure out what the number is for your hardware. You'll know when it hits you because your connections randomly get really slow, but it's really hard to debug if you don't know that this is going to happen. Another big word of warning, do turn off generic receive offload. The generic receive offload is a mechanism that the kernel uses together with the network card, especially if you have an expensive Intel NIC, to reduce the load on the packet processing by coalescing packets in the network card and then sending them to the application as one big packet. That works great when your application is actually on the host, but with IPVS, it just corrupts the packets. And for weird reasons, it doesn't do it all the time. We've repeatedly run into issues where suddenly, magically, everything stopped working, and then it turned out that, yeah, GRO was enabled on one of the load balancers. So this is something to keep in mind. There are various Linux kernel versions that claim to have fixed this issue. Don't trust them. We stopped doing. We just turned it off. And even when the third changelog says this is now fixed, we don't believe it. We just keep it off. It doesn't help anyway in this use case. All right, so now we have 2 layers of load balancing in front of our app, just so we can shift all the traffic around. Yeah. This stack is still our stack for the mothership, but in parallel, we started breaking out services into we started moving towards microservices. This mostly the reason for that was mostly the development velocity. But it meant that we had a much, much more internal traffic to deal with. And this was the stack that we knew, so we cloned this stack to front our internal platform as a service where all the microservices ran. Now, these microservices talk to the mothership. The microservices talk to each other all the time. So we ended up with a huge blowout of a huge blow-up of how much traffic we needed to load balance, to the point where a single request from a user would blow up into many, many, many requests that all traverse these same load balancers again and again and again. This becomes very unstable over time because a little disturbance in this leads to even more open connections, and which makes it even slower, which leads to even more connections. Everything falls over, and there is no way to fix it other than restarting everything. So we had to somehow, we came to a point where load balancing did not work anymore for us. We were almost at the point where we had more load balancers than we had application servers behind these load balancers. That didn't, we couldn't go on this way. So we pulled the handbrakes. Luckily, we already had everything lined up. We just didn't pay attention and didn't configure our applications right. We have a DNS service discovery mechanism. It's backed by console with a bit of our own semantics slapped on top. That doesn't really matter so much. The gist of it is most of our applications by that time were based on Twitter's Finagle library, which has really, really good client-side load balancing support. So we could just tell, instead of telling the application, talk to this one name, which then happens to be a load balancer that distributes it to all the other instances, we just told it, here's how you find all the instances, and let the client-side load balancer handle it. That you can't always do that. This requires very good support in your application to be able to actually do this. Otherwise, your load distribution is going to go to hell. And it did. We had a few where we tried to migrate to this, and it didn't work, and the load distribution went to hell. So this is also why we still do need load balancing. So we also started then using the same load balancing to load balance over load balancers, so we could eliminate IPVS from this part of the stack. We moved the Nginx onto the actual app servers, so that by using Passenger. Passenger is a way to run either Ruby or Python apps basically inside of an Nginx process, and it manages these for you. It can manage the only one request at a time constraint. So we can now treat these bundles of multiple app instances behind a Passenger as one application instance that you can't just talk to, and you don't have to worry about concurrency anymore. So this is how we got around to actually fixing Rails. So now we can actually just go and DNS load balance over all, or client-side load balance over all of these. So we've kind of come full circle, but kind of not. That's it. There is an RFC. If you're using the wrong glibc version, then and you return a DNS result set with multiple DNS addresses, it's even worse than random. It picks the closest IP address, which then makes, which is suddenly one of our database servers, again, try to take 3 times as much traffic as everything else, just because more clients happen to be closer to it network-wise. So this is something to be aware of. That's why we still need load balancers today for load balancing databases. I think I need to skip the bonus round. We did some routing of virtual IPs in a routed data center. So our data center is no longer a big flat layer 2. So we had to do some routing magic or some routing work to make that work. If you want to know more about that, come talk to me in the break. And now it's time for questions.
Any questions? Yes,
no.
no.
I want to throw this one.
They told us we have to use this one, so. No? All right. Thanks,
All right.
Matthias.
The credits, I built none of this. I've always just been maintaining and standing on the shoulders of giants, specifically these people. I have a little reading list in the slides, at the end of the slides, and you can give feedback, and here's a link to the slides.
Thank you.